तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
This is the second lecture on the topic of bipolar junction transistor, and this is the 27th lecture of this course. In the previous lecture, we have seen the characteristics that we want to explain for this particular device. Then we saw briefly what is the historical set of events which gave rise to the development of this device. Then we also saw the real structure of a modern bipolar junction transistor and its approximate structure, which we are going to use in the analysis of this particular course. So this was the structure that we said we are going to use in our analysis. So here the emitter region and the collector region and the base region, all the three regions are uniformly doped. Further, the emitter and collector regions are sufficiently long so that the excess carrier concentrations, if any, in these two regions decay to 0 by the time you reach the contacts. Now for this particular structure, we will develop the transistor action. Now when we develop the transistor action, we will start with a simple biasing arrangement as shown in this diagram. So here we will assume that emitter and base are forward biased, the emitter to base junction is forward biased, and the base to collector junction is 0 biased or shorted. So this is a simple biasing arrangement. Further, in this analysis what we will do is that we will ignore the space charge region widths for simplicity. Later on we will include these widths when we need them. So emitter base junction voltage is indicated as VEB. This is the emitter terminal, this is the base terminal, and this is the collector terminal. Now what we will do is that we will be doing a thought experiment. So this experiment will involve moving the collector junction to far away locations from the emitter junction and then slowly bringing the collector junction closer and closer to the emitter junction, and then seeing what happens to the various currents in the device and in the terminals. So when this particular collector junction is very far away, for that condition we can show the excess carrier concentrations in the device for this biasing arrangement as follows. We are using the basic PN junction theory here. Since the emitter base junction is forward biased, we can show the excess carrier concentrations like this. So this is for collector junction moved far away, so maybe somewhere here, so that by the time the excess carrier concentrations reach this point, they have already dropped to almost 0. Now when we say the collector junction is far away from the emitter junction, we have to give some feel for what is the distance. Now from the PN junction theory, we know that excess carrier concentrations decay exponentially with a characteristic length called the diffusion length. So long as the width of this region, which is the base region, so this we will call as the base width. Since there is no space charge region shown here, WB is same as the distance between the junctions, but actually it is the distance between the two depletion edges. So WB is much greater than LB for this case. That is the meaning of the collector junction being very far away from the emitter junction. So let us say this is number 1. This is the curve number 1. So 1 corresponds to WB upon LB much greater than 1. Now, as you move the collector junction closer, let us say we come to this point, supposing the collector junction is somewhere here. Then your excess carrier concentration can be shown to be as follows. It is something like this. Notice that the boundary value of the excess carrier concentration is governed by the voltage across the junction, applied voltage across the junction. So this is the P region, for example. Minority carrier concentration is electrons here. So the excess carrier concentration we will indicate as capital delta N suffix E at the emitter junction on the P side boundary. So delta Ne is the maximum value of the excess carrier concentration, or the boundary value of the excess carrier concentration of electrons on the P side. Similarly, this we will denote as delta P E. This is the boundary value of the excess hole concentration at the emitter junction on the N side. When you come to the collector junction, the boundary value of the excess carrier concentration is 0 on either side because this junction is shorted or zero biased. So that is what is seen here. So we are not showing the electron concentration on the P side because excess electron concentration is 0 because the junction is zero biased. Similarly, boundary value of the excess hole concentration at this collector junction is also 0, either here or there. So this is, let us say, the curve 2, which corresponds to a slightly lower value of WB or lower value of WB by LB. Finally, if your base width is brought very close, the base width is reduced drastically so that you have the condition WB by LB much less than 1. This is the other extreme. WB by LB much less than 1, that is somewhere here. Then your excess carrier concentration will look something like this. This is 3. Where the base width has been reduced drastically. So the excess carrier concentrations for varying base width are shown here. The third experiment we are doing is that we want to find out how the variation of WB from very high values to very low values affect the various currents in the device. To see the currents, we must make use of the flow diagram. You recall, when we discussed the PN junction diode, we drew a flow diagram showing the flow of holes from P to N region under forward bias, and similarly for forward bias also the flow of electrons from N to P regions. So this is what we will do here. The flow diagram now can be drawn based on the excess carrier concentrations. So here the flow diagram for the emitter junction would be something like this. The emitter injects holes into the base and the base injects electrons into the emitter. So here we are showing the direction of movement of the carriers. This is dotted line shows electrons, solid line shows holes. Please note that for electrons the direction of current is opposite to the direction of flow. So what we are drawing here is a flow diagram based on this same simple p-n junction theory that we have developed earlier. Now what happens to these electrons? Because this region is sufficiently long, all the electrons recombine. That is what is seen here also. The excess electron concentration is going to 0 by the time you reach this contact. So the electrons all recombine in this region, that will be shown here as follows. So these recombine with holes which are supplied from this contact. This is the emitter contact. So the emitter contact provides for holes which recombine with the electrons which are injected, and it also provides for holes which are injected into the base or the n plus region here. Now what happens to these holes? If you take the curve 1, excess carrier distribution 1, the hole current at this edge is given by the slope of this distribution, which is almost 0, because WB, that is, this is the base width for this particular case, case number 1, is so large, the excess hole concentration here is going to 0, and slope of this concentration also goes to 0. Now we know from p-n junction theory that the current in a bipolar transistor is because of diffusion in the neutral regions and diffusion of minority carriers, which means that the current depends on the gradient of the excess carrier concentration. So the diffusion current of holes here is 0, which means all the holes which have injected into the n plus region or base have all recombined for this particular situation. So for case 1, the picture will be all these holes recombine. So obviously they recombine with electrons which are supplied from the base contact. So the base clearly is supplying for electrons to recombine with the holes injected from the emitter, and it is also supplying for electrons to be injected into the emitter. This particular component of the emitter current, which is due to holes, we will indicate as IEP, and this current, which is because of electrons injected from base to emitter, will represent as IEN, and this summation of these two currents is IE. So in order to avoid cluttering, I will remove these symbols which indicate electron and hole currents. So this will be the picture for case 1, WB by LB much greater than 1. As you reduce your WB, supposing we come to the curve 2, the situation 2, where WB by LB is around 1, we can say. Then you find that now the slope of this distribution of holes here is not 0. This particular slope is not really 0. So the slope has increased as compared to this case, which means that all the holes which have been injected from emitter to base are not recombining within the base. Some of these are reaching the collector. This is obvious because the base width is now small. In this region, all the holes which are injected, they are not able to recombine during the diffusion. So what it means is that for case 2, we must show a current of holes being injected from base to collector. This is very important to understand. So this particular slope indicates that there is a movement of holes from base to collector. This is location of the junction for case 2. Now here, while drawing the flow diagram, we will not show the locations of the junction separately for these 3 cases, because that will clutter the diagram. So what we will do is we will assume that the collector junction is located somewhere here, and we are not concerned about the location. So we should not try to link this diagram and this diagram. So all that it means is we are going to say that this is the base region and we are going to show what happens within the base region and in the collector region. So this junction may be movable as shown here. Now for case 2, not all the whole current is recombining, some of it is reaching here. So this is a general situation. We can regard the case 2 as a general situation whose one extreme is this, that is WB by LB much greater than 1, and the other extreme is this, which is WB by LB much less than 1. So here this current which is reaching the collector is called IC, and since this is because of holes, it is ICP. So this is your collector contact. Notice that even for case 2 we have not drawn any electron concentration in the p region, any excess electron concentration in the p region, because this is zero biased, excess electron concentration is 0 at the boundary of this junction, and it is 0 everywhere else also. So there is no electron current in the collector. So that is why you do not have any ICN for collector base junction equal collector base junction bias equal to 0. Now let us indicate the whole current recombining in the base by the symbol IR. So this is your base current IB, which is nothing but IR plus IEN. The role of the base is to supply electrons for recombination with the holes which are injected from p region and for injection of electrons into the p region. That is what this shows. So this flow diagram which is shown is generally applicable to all the cases 1, 2 and 3, except that the values of these currents are different for these 3 cases. So for case 1, ICP is negligible or 0, so that IEP is equal to IR. For case 3, what we will find is that this slope here at the emitter junction and the slope of the whole distribution at the collector junction are almost the same. So this looks like a straight line for very small base width. This you can understand also in a different way as follows. You know that the excess carrier distribution decays exponentially. So e power minus x by LP, something like that, or x by LB in this case, because the diffusion length of minority carriers in the base is LB. This LB is the diffusion length of minority carriers in the base. So for x by LB much less than 1, you know that exponential of minus x by LB much less than 1 exponential of minus x by LB, where x by LB is much less than 1, can be approximated as 1 minus x by LB. So this means that the exponential decay will be almost linear for very small values of x. This is what is seen here. Okay, so if your WB is very small compared to LB, this is the situation, then it will almost be a straight line. So this slope and that slope will almost be same. That is what is shown here. So we can see this mathematically, or we can see this geometrically. In fact, geometrical interpretation is much easier to understand and is much more vivid. So for this limiting case of WB by LB very small, the recombination current will be very, very small. The recombination current depends on the area under the excess carrier distribution. In fact, it is the area under the excess carrier distribution divided by the lifetime in that region. We will see this in detail later. But for now, qualitatively we need to understand how the various current components IEP, IEN, IR and ICP, and therefore the emitter, the base and the collector currents. So the ICP here is same as IC. How these components change when you change the base width? That is the purpose of our analysis. Now based on the simple PN junction theory that we have developed, which says that the currents at the junction are because of diffusion of minority carriers, and therefore at the junction depletion region boundary the current can be estimated from the slope of the excess carrier distribution. We can get the variations in the various current components as the base width is reduced in our thought experiment. So we will summarize these results on this particular on this experiment here. So we are maintaining VEB constant. So this voltage VEB is maintained constant as you change your WB. So as WB by LB is reduced, this arrow downward indicates reduction. So progressive reduction up to WB by LB tending to 0. So now we will write what happens to the various current components. Let us take the current IE, that is this current. So this IE is IEP plus IEN. I want to emphasize that arrow here indicates the direction of flow of carriers, and since dotted line is for electrons, the flow of electrons is in this direction, but the flow of but the current because of electrons is in the other direction. So which is the same as the current because of holes. So both these currents add up. So IE is equal to IEP plus IEN. Now as you reduce WB, you find that the slope of the whole concentration in the base is going on increasing. This is very clear. So for case 1 your slope is less, for case 2 it is more, and then for case 3 it is even more. This can be seen from here. The slope is going on increasing as you reduce WB. Whereas since VB is maintained constant, the boundary value however of the excess carrier concentration is constant, it does not change. So on the emitter side the distribution of electrons is not really changing, or the distribution of excess carriers is not changing. So this means that the slope here is also not changing, and therefore IEN remains constant. So VB equal to constant means IEN is constant even as you change WB, but IEP goes on increasing as you see from the slope. So this is what we will write here. IE is equal to IEP plus IEN, where IE goes on increasing because IEP increases, but IEN remains constant. Let us repeat the same thing for collector current IC, which is equal to ICP in this case. So IC is nothing but ICP. For very large WB, ICP is 0 because the slope is 0. As you go on reducing your base width, the slope goes on increasing from 0. You can see this progressively, this slope and this slope. So we can write IC increases because ICP increases. Now what happens to IB? You can see that IB is IEN plus IR, of which IN is constant, and IR reduces as you reduce your base width because IR is difference between IEP and ICP. That is the same as the difference between the two slopes. So this slope and that slope. Now you can see that these two slopes are progressively becoming closer and closer as you reduce your WB. So the difference between this slope and the slope here is less as compared to the difference between this slope and the slope here, and it is further less when you come to the curve 3. So this slope is almost same as that slope. This is very evident. Alternately, one could also see the area under the curve, because as we said IR is nothing but the area under this curve, excess carrier concentration, divided by the lifetime. We will explain this a little bit more clearly later. Since IR is proportional to the area under the curve, it is very clear the area under the excess carrier concentration goes on reducing as you reduce the base width. So IR is reducing while IEN is constant. So IB is going to reduce. So IB falls because IB is equal to IR, which is falling, plus IEN, which is constant. Now it is of interest to see that the forward bias junction is creating a current in the neighboring junction even though that junction is zero biased as you reduce WB. That is what is seen from here. So part of the emitter current is coming to the collector as the junction is brought closer and closer, okay, and the part which is coming in the collector is increasing as WB reduces. Now at this point I also want to explain why the terminals are called emitter, base and collector. It is very clear from here that this contact is called emitter because it seems to be emitting the current of both holes and electrons, but in a PNP transistor it is mostly holes. Clearly IEP is much greater than IEN. This is clear here because doping here is much more than doping here. Doping here is Ne, which is much more than doping here, which is Nb, is much greater than doping here, which is Nc. So Ne is much greater than Nb, is much greater than Nc. So because of this, the hole current here is much greater than electron current. Anyway, the emitter is injecting the current. Now part of the hole current that is injected is reaching this contact. It is collecting the current that is remaining after transition through the base, after moving through the base. That is why this contact is called the collector. It is collecting the holes which do not recombine in the base, and this is the base contact, because if you recall the diagram that we had shown in the previous lecture in the historical development, the emitter and collector contacts were on a semiconductor substrate or a base. That is why that third terminal apart from emitter and collector came to be regarded as a base, or it is called a base. So because of this particular condition for the various currents, it is of interest to know what is the ratio of the collector current to the emitter current. Now to write this, we should recognize that part of the emitter current is the hole current, and part of this hole current is this hole current which is reaching the collector. So therefore we can write two ratios. One is IEP by IE. What happens to this ratio? This ratio is called the injection efficiency, and it is denoted by the symbol gamma. So gamma is injection efficiency. Now why is it called injection efficiency? Very simple. It is only the holes which are responsible for the current in the collector. These electrons are not responsible for the whole for the current here. So if the emitter is efficient, most of the emitter current should be because of holes, so that at least some part of it can be collected, because this electron current you are not able to collect at the collector. So if you want efficient device, then IEP by the total current shows the efficiency. That is why it is called injection efficiency. Let me rub this off to avoid cluttering. So IEP by IE we can write as IE is IEP plus IEN. So this is same as IEP by IEP plus IEN, which is nothing but we can write this as 1 upon 1 plus IEN by IEP. Now we can see what is happening to this injection efficiency. You see that IEP is increasing but IEN is constant. So IEN is constant and IEP is increasing. So which means IEN by IEP is reducing. So 1 by 1 plus IEN by IEP is increasing. So you find injection efficiency is increasing. And for the limiting case of very small WB, when the WB is very small, you see that the slope is very large. So your IEP is large, as much larger compared to IEN. So therefore we can say that this quantity tends to unity, because this quantity tends to 0 as WB is reduced. So injection efficiency becomes close to 1. The second ratio of interest is the ratio ICP upon IE, upon IEP, not IE, IEP. So what fraction of IEP is reaching the collector, because a part of it is recombining in the base. If recombination is very small, the entire IEP will reach the collector, and this way almost the entire ammeter current will reach the collector if this IN is small. So that is why this is another ratio of interest, and we can write this as, we will write this using the symbol B. This is called base transport factor. It is called base transport factor because it represents what fraction of the current recombines when the holes are transported across the base, or what fraction of the current is still retained even after transport across the base. So ICP by IEP we can write as IEP minus IR upon IEP. So ICP is IEP minus IR. Now what is this? This we can write as 1 minus IR by IEP. Now as shown here, IR is already falling as WB by LB is reduced, and IEP is increasing. So this is falling and this is increasing. So obviously this ratio goes on falling, and in the limit of WB by LB very small, in fact this ratio will become almost 0. The recombination current here, which is dependent on the area under this curve, that is this area, will almost become negligible. So this factor also will tend to 1. And we can now write the ratio ICP upon IE, which is normally called the alpha of the transistor, and this alpha is nothing but gamma into B. This is clear from here. If I multiply this ratio and this ratio, IEP will cancel, you will get ICP by IE. Now this ratio ICP by IE, it tends to 1. This is very clear from here as WB by LB reduces. So as WB by LB reduces, this alpha of the transistor tends to 1, and this ICP by IE is nothing but IC by IE. So this quantity is IC for this particular case. So the transfer of current from emitter to collector is almost complete for these conditions. Now I want to emphasize what are the conditions for this. The IEN should be much less than IEP, that is the first condition, so that almost entire IE is IEP, and the base width should be very very small as compared to diffusion length of minority carriers in this region, so that the IR is very small. So that entire IEP reaches the ICP. Under those conditions, under these two conditions, the collector will collect almost the entire emitter current. Now this transfer of current from a forward biased emitter junction to a zero biased collector junction is the transistor action. Okay, this is called the transistor action. Let us understand the word transistor itself in the light of this explanation. The word transistor has been derived by actually bridging together two words as follows: transfer resistor. So you remove the FER of this word and RES of the next word. So you have transistor. Okay, so transistor, that is how the word transistor is derived. This and this you collect. Transfer resistor, the transfer of current from emitter junction to collector junction. This is being referred to as a transfer resistor device. Why? Because look at the resistance of these two junctions. A forward bias junction obviously has a lower resistance than a zero bias junction. So you are transferring the current from across a lower resistor to a higher resistance. Now obviously if you transfer the current from a low resistance to the high resistance and during the transfer you do not lose the current, evidently you are going to have a gain in the voltage and power. Okay. So for example, if you take the power is I square R, depends on the current and the resistance. So higher the resistance, if the current is same, higher the power. So because of this particular action of transferring of the current from a low resistance to a high resistance, which looks like some kind of an amplification. So to emphasize this fact, this device is called a transfer resistor or a transistor. Now this is the basic transistor action: transfer of current from a forward biased emitter to a zero biased collector, or from a low resistance junction to a high resistance junction. And the basic parameter associated with this transfer is alpha, and this alpha is close to 1 if the doping in the base is less than that of the emitter. That is one very important condition, because only under that condition this concentration here will be much less than this concentration. The electron concentration will be much less than the whole concentration, and that is IEN will be much less than IEP, and the base width should be very small. So necessary conditions for transistor action are NE much greater than NB and WB much less than LB. So because of this, your injection efficiency is high and the base transport factor is also high. Recombination base in base is small and the electron current into the emitter is small. So under those conditions, alpha will be high and close to 1. Now one can also define another parameter called the beta, okay, because just as we can define IC by IE, we could also define the ratio IC by IB. IB is given here. So IC by IB, you can very easily see it can be written as IC upon IE, which is the alpha, by IB by IE which is further written as IC by IE by IB is nothing but IE minus IC. IB is nothing but, let us look at this, IB is nothing but IE minus IC. So direction of currents are like this, IE, IC and IB. So let us remove this to avoid cluttering. This IB is difference of IE and IC. So that is what is written here. So this is nothing but IC by IE is alpha, so alpha by 1 minus alpha. This quantity is called beta. Now if alpha is very close to 1, you can see beta is very, very large. Now having discussed the situation for collector base voltage equal to 0, let us see what will happen if you apply a bias between the collector and base regions. Okay? So here we have assumed that the collector and base were shorted. Now we want to introduce a power supply here and see the effects of this power supply, which can either cause a forward bias across the junction or a reverse bias. So let us start with the effect of the forward bias. So this is what we have shown here. The collector to base junction is forward biased and we are increasing the forward bias from 0 onwards. So what will happen? Now we will assume that the base width is very, very small, because that is the condition in a practical device, so that entire emitter current or almost the entire emitter current is transferred to the collector. So WB by LB is much less than 1 and we will keep the emitter base voltage constant. What happens as you increase the collector base forward bias? So for collector base 0 bias, your excess carrier concentrations would be something like this. So this is close to a straight line. This is delta PE and this is delta NE on this side. This is for collector base voltage equal to 0. If your collector base voltage is now positive or there is a forward bias, you will have the following situation. The boundary value of the excess carrier concentration will increase on either side of the junction. So your whole concentration on the N side has increased and you are also going to have excess electrons on the P side, and since doping in the collector is lower than doping in the base, your excess carrier concentration of electrons in the collector will be more. So this is the kind of situation. For forward bias across the collector base junction. So this is VCB equal to 0 and these two correspond to VCB greater than 0. Now for VCB equal to 0, this was the flow diagram. There were no electrons in the collector, there was no electron current. But now you can see from here that ICP exists because you do have a slope of holes at this junction, even for collector base forward bias. But in addition you also have ICN because the electron concentration also is raised. Now the current because of electrons is related to the initial slope of this carrier distribution. Now what is interesting is that this means that the electrons are also injected from base to collector. Like holes are injected from base to collector as shown by this slope here. This slope here shows electrons are injected also from collector base to collector in the same direction. So the electrons are also moving in this direction, in the same direction as collector current. And what will happen to this electron current? Obviously it will recombine in the collector with the holes. So what do you see now? If you have electrons moving in the same direction of holes, then the electron current will be opposite to the direction of hole current, because electron current is opposite to the direction of flow of electrons. So you can see from here that the electron current is subtracting from this hole current. Okay? So this current is subtracting from this current, and as a result your collector current is actually falling when you have a forward bias applied. So this is your ICN, and as you increase the forward bias, this component will go on increasing exponentially with respect to the voltage, because the boundary value of excess carrier concentration rises exponentially with respect to the forward bias. So that is really a bad situation, because rapidly as you increase the forward bias, this current will start increasing, and therefore it will subtract from this particular hole current which is injected, and your collector current will start falling. And you can have a situation where the collector current becomes 0 and it even becomes negative. That means the collector current in this direction is reducing, it is becoming 0, and the collector current may start flowing into the collector. So therefore the forward bias destroys the transistor action. It destroys the effect of the transfer of current from emitter to collector, this particular phenomenon. So forward bias across the collector base junction is not really beneficial for the transistor action. So we can show this here. When you keep VB constant and for very small base width, which is a practical situation in the transistor, as you increase your collector base forward bias, what happens is IEP, that is IEP is dependent on the slope of this particular distribution at the emitter junction. So this IEP is falling, you can see that the slope is falling as your excess carrier concentration starts rising near the collector base junction. So IEP falls and therefore IE falls. Now IC is ICP plus ICN, but ICN is negative in polarity. Please note this here. So ICN is in opposite direction to ICP. Flow of electrons and holes in the same direction means their currents cancel. So ICP plus ICN is nothing but ICP minus modulus of ICN. So what is happening to ICP? This is falling. You can see from here that this current falls. You can see the slope is reducing. This slope is more, this slope is less as you increase the forward bias. So ICP falls, whereas magnitude of ICN rises. So magnitude rises. So what we will do is, instead of showing this here, we will show it here. So ICP is falling and this magnitude of ICN is rising. So the difference is really falling. Okay. So that is why IC can become 0 and it can become negative also, because this quantity can become more than this quantity. And what happens to IB? You can see from here that the area under this curve is going on increasing. Area under the excess distribution in the base is going on increasing. So IR is going to increase. So IR increases, and base current now is not simply IR plus IEN, which was the situation for collector base voltage equal to 0. You also have another component here, that is plus ICN modulus, because you can see from here that base is now also supplying electrons to the collector. So your base current has really increased tremendously. It is this current plus this current plus this current. So that is what is shown here. So IEN is constant, but this ICN is increasing. So IB increases, whereas IC falls. So this is really undesirable. Each of these things is undesirable. So the transistor action is destroyed if you have forward bias across the collector base junction. So this is not desirable. Now let us see whether a reverse bias is acceptable. What happens if you have reverse bias? So this is what is shown here, collector base junction voltage less than 0. Now when you increase the reverse bias, the depletion width goes on increasing and its effect needs to be considered, because a part of the depletion region is in the base and a change in the depletion region would mean a change in the base width. Now for simplicity we have not shown the emitter base depletion region, which is also there, okay, but this depletion region will be more significant compared to this, obviously, because this is reverse bias and it can go on increasing, whereas your forward bias cannot change very much, okay. So your depletion region here will not change much, that is why it is not shown. So the base width, electrical base width, which is this, will go on changing as you change your reverse bias. So that is one of the effects, but then we have to see whether it affects the transistor action. So let us plot the excess carrier concentration for collector base reverse bias. This will be as follows. So this is the depletion edge. So here you will have a small negative excess carrier concentration equal to the minority carrier concentration, because there is a reverse bias. We will assume this VCB is greater than 3 times Vt. So reverse bias is more than 3 times Vt. So the excess carrier concentration will saturate at a negative value, and here similarly you have like this is excess carrier concentration saturating at again minority carrier, magnitude is minority carrier concentration. Since doping here is less than doping here, this value is more than this, because minority carrier concentration in collector is more than in base. So this is delta PE, this is delta NE, this is minus delta NC, and this is nothing but, in fact, we can write this as minus electron concentration in the collector. So NP0, where this corresponds to collector, and this is minus PN0, corresponds to base. They are really small. In fact, if you show to scale, you cannot really show this value, because this will be much more than this, and this is a linear scale. So what is the result of this? The result of this is, now this means that there is a small current here, ICN, but it is in the opposite direction to what it was when there was a forward bias. So forward bias, the electron current was injected from base to collector, but for reverse bias it is the other way around. This is clearly evident from this slope. This slope indicates that you have flow of electrons like this. So this is really a generation current, but this current will be small because it is only dependent on the minority carrier concentration, and it saturates. You know that the reverse current across a diode saturates, okay, if you neglect the generation within the depletion layer of that junction. So this is the so called ICN. Now we will show this by the symbol ICO, which is commonly used symbol for the reverse current across the collector base junction of the bipolar transistor. So you can see now that ICP is not significantly affected, because this point is no different from this point, which was the situation for 0 collector base voltage. So this is not very different, except that it has shifted a little bit on this side because of the change in the base width. So what you find is ICP is not affected very much as compared to 0 bias, and ICN, which is this component which has come in, is really very, very small, because it is the reverse current of a diode. So in effect what we can say is that the collector current is not significantly affected by the presence of reverse bias. Okay. Now if the reverse bias is very large, of course this junction can break down, but so long as we don't go to such high voltages, we find that the transistor action is essentially remaining unaffected. The only difference is that there is a small additional current in the collector, that is a reverse saturation current of the collector base junction, in addition to the situation we had for zero bias. So all that is happening is we can write IC equal to ICP plus ICN, and ICP is no different from what we had in the zero bias. So IC is nothing but alpha times IE. Please recall that under zero bias ICP was alpha times IE, and plus this ICN now is IC naught, which is the symbol for ICN normally used. Now the junction, the current across the reverse bias junction will also be due to some small amount of holes on this side. This is shown by the fact that this hole concentration has reduced a little bit, but this effect we can neglect because minority carrier concentration on the collector is much more than that in the base, so we neglect that effect. So we can write IC equal to alpha times IE plus ICO for reverse bias across the collector base junction. So reverse bias across collector base junction is acceptable so long as it doesn't lead to breakdown. Now with that we complete the basics of transistor action, in which what we have shown is that zero bias across the collector base junction and forward bias across the emitter base junction leads to a transfer of current from the emitter to the collector. This transfer is almost complete, and if you change the collector base junction bias to forward from zero bias, the transistor action is destroyed, but if you change it to reverse bias, so long as the reverse bias is below breakdown, transistor action remains essentially unaffected. We will now continue with the other aspects of transistor action in the next class.